Geometry. What is geometry? Some people know. I actually don't have any idea what geometry is. Is what partly made it hard to do this, to put this talk together. Because like you learn enough geometry and you realize I don't actually know what geometry is anymore. Anyway, but I can tell you some things about geometry. Alright. Basically, it's about points and lines. You probably already knew that. But this diagram sort of hints at what points and lines are, but we might want to actually know, what are points and lines? Click. There we go. What are points and lines? Anybody have an idea what a point and a line are? I just want to hear some ideas.
Line is 2 points and the connection between them.
Connection between 2 points. Okay, that's actually a very good answer. I hope you know why. You.
Infinite amount of points?
Infinite number of points. Okay, that's interesting. Anybody else have an idea what a point is?
A location in space.
A location in space. Very good answer. Okay. So, basically, Euclid had some ideas about what points and lines were. Does anyone know what Euclid's ideas were?
Not very good ones.
Yes! But that's kind of jumping the gun a little bit, as they say. Euclid said, a point is that which has no part. And a line is breadthless length. And a straight line is a line that lies evenly with the points in itself. Now, what the heck is he talking about? Nobody even knows. And he doesn't even know. I mean, basically, this is not mathematics. They are their properties and nothing more. It's kind of existential, but basically, they are how they behave. Anything can be a point as long as it satisfies the axioms for a point. Anything can be a line if it satisfies the axioms for a line. There is, anyway, I'll get to it later. Yeah. So, let's talk about some axioms, because basically, the best way to start with geometry is to build it up from axioms, which are things that we just take to be true because we want them to be. Okay, there are at least 3 non-collinear points. This is a kind of lame axiom. It basically says that you don't have a geometry that consists of 1 line and 1 point, because that's boring. That's basically, also, when I learned non-Euclidean geometry, this was called the Robert Mugabe geometry, because a lot of lines were called committees a long time ago. Basically, there's a ton of committees, one person's on all of them, and that's it. It's the Robert Mugabe government. There's no point in studying that geometry. So we want at least 3 non-collinear points. So we have at least a triangle in our geometry. Otherwise, what's the point, right? Okay, every line contains at least 2 points. That rules out Robert Mugabe. I mean, that's kind of an old joke, but because he's out already. Okay, now things start to get in. These are just bookkeeping axioms. 2 points determine a unique line. So, if you have 2 points, there's a function that takes those 2 points and gives you a line, whatever a line is. Now, you can call it the line that passes through those 2 points, or you might want to call it the intersection of those 2 points. You usually talk about intersection of lines, but it's just words. Alright, given a line and a point not on that line, there's a unique line containing that point, which does not intersect the first line. To intersect means that they have a point in common. So basically, we want to think about lines as sets of points. And intersection means, well, centered intersection. They have a point in common. Now this last one that I put down is Playfair's axiom. A mathematician. Anyway, this is essentially Euclid's parallelism axiom. It's about parallelism. Anyway, so these are the axioms for affine geometry. Now you may have noticed there's no distance talked about. There's no angle. What is geometry without distance and angle? Well, it turns out geometry is a lot of things without distance and angle, and that's just fine. This is sort of the finite affine geometry is basically a more general form of Euclidean geometry. So out of this sort of general affine geometry, we can come up with a bunch of different geometries that are all affine geometries. And just because I bet a lot of you don't know what the word affine means. It essentially means a linear transformation plus a constant. So a linear transformation has to take the zero vector thing, whatever element is zero, to the zero thing, right? Because it's linear, we all know that. An affine transformation can look like, essentially y equals mx plus b is an affine function, not a linear function. You were told wrong, basically. And yeah, basically math teachers lie to you all the time. And I'm actually lying to you now, you'll see in just a minute. Alright, so it's these last two axioms that basically where all the fun comes from. 2 points determining a unique line, we'll see about that. Given a line a unique point, the unique parallel that I talked about, we'll see about that. That's where all the fun comes in geometry, basically. Alright. Now, inspired from Euclidean geometry, we can define things like addition, given this just completely basic set of axioms. So in Euclidean geometry, we'd want to add these lengths together, the length of 0 to A and the length from 0 to B. Now, to do addition, you need to decide where 0 is. You need to, and that's a completely arbitrary decision, but it needs to be done. Like, where you put your origin on your axis, completely arbitrary, but you have to do it to make sense of what addition is. Alright, so now how do we do this? Well, there's only a few things we can do. We can construct parallel lines, and we know there's at least 3 non-collinear points. So we know there's a point out here somewhere, not on this line. So let's just choose one of them. We'll call it P. Sorry. And from the parallelism axiom, we know there's a line that goes through it that's parallel to the first line. Since 2 points determine a unique line, we can draw this line. So this seems like a sort of like, if you write it out step by step, it seems like a pretty arbitrary prescription for addition. But then given that, we can construct this parallel line through here. You can show, I'm not going to bother doing it, that this line is not parallel to this line. Without any notion of angle, you can show this. So essentially, in Euclidean geometry, which is where this algorithm inspiration comes from, we're taking this length and just translating it up there. Right? We want to add this length to this length, so we can put it up here and then bring it back down here, is what we're going to do. But this is without any notion of length that we're doing this. So since these lines are not parallel, we can construct their intersection. We can just talk about their intersection as P prime. And then we can construct the line between those 2 points and construct its parallel. And again, you can show that it's not parallel to this line and thus has an intersection. We'll call it an intersection A equals B.
Huh.
This is how you do addition in geometry. Wow. You just take this line, put it over there. Simple enough. Now, who's like, wait a second, something's fishy. What's fishy about this? Well, it seems so logical that you probably don't realize, but like, is this well defined at all? I said just choose some point P. How do we know that it's not going to be different if I choose P prime as P? And then, like, exactly, like, wait a second, arbitrary choice, not a good sign. It turns out it's because I lied to you. And there's a 5th axiom of affine geometry called Desargues' axiom, which basically says addition is well defined. I mean, you use it to prove that addition is well defined, but it basically says if you have 2 triangles and the lines that go through their vertices are all parallel, and these 2 lines, the black lines here are parallel, then the red lines are also parallel. And you need this axiom to show that addition is well defined. Otherwise you get things like the Moulton plane, which is just like, makes everything cumbersome to deal with because addition isn't well defined. So, yeah, we'll just take, I mean, it's often called Desargues' theorem because it's a theorem of Euclidean geometry, but for like affine geometry, you need to take it as an axiom. Anyway, there's 2 different versions. One where the triangles are similar and one where they're congruent. And when they're congruent, they're 3 parallel lines or 3 concurrent lines. Now, it turns out this all comes from projective geometry, which is the study of perspective, which is why like parallel lines and congruent lines were the same thing. Anyway, we'll get to that later. Alright, it turns out you can define multiplication too. So like, I'm not going to go through step by step, but basically you need to decide what's going to be your 1 and what's going to be your 0, and then you can multiply things. The choice of 1 and 0 is, again, completely arbitrary, but like the choice of units is always arbitrary. Choice of origin is always arbitrary, so that doesn't mean anything. But yeah, I hope you can see what the steps are. You choose some arbitrary point P, construct the line from 1 to P. Well, first you construct the line from 0 to P, then you construct the line from 1 to P, construct the parallel through A, and then run the line from here through B, and then the parallel through P prime, and see where it intersects, and that's A times B. We're going to define that. Now, this is actually, in Euclidean geometry, this is a multiplication of lengths. Again, the inspiration for the algorithm. And you can see why this actually multiplies lengths because of similar triangles, basically. Like the green triangle, which is underneath the orange triangle, is similar to the orange triangle, and thus the lengths are all multiples of each other, so it has to multiply. That's cool. And again, so for this, to prove that this is well defined, again we choose an arbitrary point P. You want Pappus's theorem, which you can look up if you're really interested. It turns out it's equivalent to Desargues' axiom, but they're really hard to show that, or really annoying to show that they're the same thing, so you often just choose them both as axioms, so you don't have to prove one from the other, because it's really annoying. But we did that in class. Alright, things that are true. So you can prove this all geometrically, given our algorithms for addition and multiplication. You can show that, well, we know 0 exists. You can show that, well, there's always, given a point A, there's always a negative A, such that when you sum them, you get 0. You can show that it doesn't matter which order you sum them, that B plus A equals A plus B. You can show that if you're summing 3 things, you could sum A plus B plus C. That's the same as A plus B plus C. And then, equivalently for multiplication, you can always show that there's, given a point not equal to 1, there's always some point that gives you, that when multiplied gives you 1. And that the order of multiplication doesn't matter. And similarly, A times B times C equals A times B plus C, B times C. And furthermore, and this, the proof of this last one is really annoying, but again, it's all done geometrically with those 5 axioms I showed you. The fact that we have enough lines and points to be happy, and the fact that 2 points determine a line, and the unique parallel. Just with those, you can show that multiplication distributes over addition. That C times A plus B equals C times A plus C times B. I'm not going to show it to you. It's a horrendous diagram, and you need to use all. It goes on and on. Anyway, these things are true. Now, anybody who's taking abstract algebra right now is going, ooh, what we have here, folks, is a field. Some common fields are like the rational numbers, the real numbers, and the complex numbers. Basically, we're going to be doing things over the real numbers because they're the easiest. So I talked about one of Euclid's mistakes was trying to define points and lines as other than just how they behaved. I mean, he had enough axioms on how they behaved to be good. But another thing he sort of assumed without realizing it was that he was always working over the real numbers. He was sort of working over the complex numbers. One of his axioms about circles, obviously pure affine geometry doesn't deal with circles yet, because we don't have any notion of distance or angle or anything like that, was that essentially if you have 2 intersecting circles, that there's a point here and here that's on both of them. That's only true if you're over the real numbers or the complex numbers. If you're over the rational numbers, like, these are essentially really finely dotted lines, and most likely they pass through each other without touching. So that was another, well, it wasn't really a mistake. It was an assumption he failed to realize he was making. But, like, he did a lot of good stuff, so. Okay, those are things that are true, just from those affine axioms. Now, the way to go about this, when you're modeling geometry, is you say, okay, this is what our points are going to be, and this is what our lines are going to be. So you specify what kind of mathematical objects your points are going to be, either in R2 or R3. I mean, you could do other things too. There's a way of defining geometry that involves functions and not like vectors, and it's, why not? But we're going to stay away from that for this lecture. And then you define what subsets of points constitute lines. And then you can define a distance function that takes 2 points and gives you a distance. And you can define an angle measure function, which given 2 lines, or rays rather, gives you an angle. And then you want to specify the 3 parameter isometry group, because like, really all this boils down to linear algebra. I mean, not linear algebra, abstract algebra at the end. But we're not really going to go there, because it's interesting enough without going there. Okay. So let's talk about what a collineation is. A collineation is a function that, given a geometry, it has lines and points. It maps points to other points in such a way, because points are our essential mathematical objects. It maps those points to other points in such a way that if points were collinear to begin with, they stay collinear. So it maps lines to lines. Now, a translation is an example of a collineation. You just shift everything, and lines stay lines. A linear, but that's not a linear function, because the origin gets moved, which can't happen for linear functions. We know that, right? So the linear collineations, turns out we can use these to determine what a rotation is. So like, how many nice 2D, because we're just talking about 2-dimensional geometry for the sake of this, how many nice 2-dimensional linear transformations are there? And by nice, there's a bunch of things I'm saying with the word nice. Basically, it doesn't scale things by any factor, so it's determinant is 1. And I guess determinant 1 is really all that I care about. It's determinant is 1, which means it's nice. It's not collapsing things. It's not flipping them around. Well, there's essentially 3 different cases if you look at the eigenvalues of this transformation. They can both be complex. They can both be real and the same number. So like you could have the characteristic polynomial of your transformation be like, lambda minus 1 squared. Which is unfortunate because you can't diagonalize it, as you probably all know, because you're taking linearity by now. Or they can be real and different. So, like, if they're complex eigenvalues, what does that mean? We've got a 2-dimensional matrix with complex eigenvalues.
Rotation.
Exactly, it's a rotation. I hope that diagram is clear. All right. Now, if they're real and the same, what does that mean? We've essentially got one eigenvector with algebraic multiplicity 2 and geometric multiplicity 1.
Shear?
Shear? Is that what you said? Somebody? Shear. Yeah, exactly. It's a shear. And real and different, well, we know that the product of the eigenvalues is 1. So we know that one of the eigenvalues is going to be less than 1, and one of the eigenvalues is going to be more than 1 for them to be different, because the product has to be 1. So it's going to be like 2.5. It means you're going to shrink in one direction and grow in the other direction. Now generally, we just take these to be, we've got an eigenvector in this direction and an eigenvector in that direction, and our axes are here. This is just the way, it doesn't have to be, but like this is the way we do it. So the transformation will look like it. It's a pretty weird transformation. And it's like squishing and pulling, and anyway. These are sort of our 3 candidates for rotation. And you're like, wait, we just showed the first one is rotation, so we're kind of done. But it turns out that's actually an arbitrary choice. We call it rotation because it's a rotation of Euclidean geometry. And that's why it's called a rotation. The other, shear, and the other one has a name that is sort of give the game away, so I'm not going to say it quite yet. Some of you may know it, but like they can all be considered rotations, just of different geometries. So another way to look at this is what sort of functions of vectors they conserve. So if a rotation, we want to conserve angle, right? Now angle and inner product are intimately linked and cannot be separated. So depending on how you define your inner product, it's going to depend on which of these is a rotation. Now, so rotation preserves inner product and therefore angle. So an inner product, which I denote with a vertical bar between the 2 vectors because I think that's a cool way of doing it, and I've seen it done in the old textbook. And like you can type it on a keyboard, you don't need the text. So the inner product basically equals some function of the angle, which I cos sub g because it's like the cosine of the angle, but like what the cosine function is depends on what geometry you're in. If you're in hyperbolic geometry, you want the hyperbolic cosine. If you're in the Galilean geometry, you want the Galilean cosine, which it turns out is really easy to calculate. Anyway, times the norm of the two vectors, right? So that's why it's so linked to angle. Now, we want the inner product to be linear in every term. And we don't want any mixing and matching. We don't want the x component of one times the y component of the other. So basically, it has to be of this form. ax1, x2 plus b, y1, y2 for the two vectors. Now, we don't want everything to be 0, so we can assume that one of them is 1. And then we just have x1 times x2. And then we have some choices for b. b can be essentially three things. It can be 1, 0, or negative 1. Because like if it was 2, then like you would just have your dimensions off and you just scale it and it's 1. But if it's a different sign than x, then that's important. And if it's 0, that's also important. Now, what's important to note is that any vector along the x-axis, we have not changed what its inner product is, and thus we have not changed what its length is, right? If the y component is 0, length is measured just the same as in Euclidean geometry, right? For any of these inner products. And this is important, because we're really only messing with angle right now. We're going to mess with the measure of length later. But distance along the x-axis is, by normal I mean just like standard, what you think of as length. All right. Now let's look at so we talked about three different possible rotations. We have the sort of two complex eigenvalues, both the same and both real and different. So now let's look at, if we take the vector 1, 0, very nice vector, what happens to it under these sort of transformations? Well, under rotation, come on, Google, there we go. It gets rotated. I bet none of you were expecting that. We measure angle actually by the area it sweeps out over the course of this transformation. Actually, twice the area, because it's 2 pi. But so that's pretty normal. So what happens under a shear? Oh, and you can relate the angle to the slope of the line with the inverse tangent function. What happens under a shear? Well, it gets sheared. It means it just like moves upwards in the y component without changing the x value. And the area, the angle, which we're finding is twice the area just equals the slope of the line. Guess which geometry, trigonometry, is really easy in, because you don't have any functions like sine and cosine, the middle one. Because theta just equals the slope of your line. All right, and the other one, it's pretty nasty, right? Under this, you're having one direction and multiplying in another. Oh, I mean overlapping. Yeah. Having one direction and multiplying in another direction. If you start here, you're gonna end up. So this was in this case, this was our vector that has a greater than 1 eigenvalue, so it like always grows in this direction and always shrinks in this direction. So if you start here, it's basically got equal components of each, but the part here is going to shrink, and it's just going to eventually become this, right? And it's just going to grow exponentially along that axis eventually. Anyway, you can talk about the area. Like this is not a trivial calculus problem to figure out what the area is here, given the slope of the line. Because this is the unit hyperbola, like it talks, hyperbolic trig identities and all that sort of stuff. Anyway, it's the inverse hyperbolic tangent of the slope, which can also be written as that. Anyone taking relativistic physics? All right, well, we'll get to that later. Okay. Now, basically, I'm going to be talking about this guy, because I don't have time to talk about all the geometries. All right. First of all, so to recap, if this is our rotation, we call it Euclidean geometry, and it's pretty standard. This is our inner product, x1 plus x2 equals plus y1 plus y2. This is called Galilean geometry, and our inner product is just x1 plus x2. This is where b equals 0. This is Minkowskian geometry after the mathematician Minkowski. And you take the difference of the products of the two dimensions rather than their sum. And that gives you essentially the inner product of vectors with themselves always equaling 1 gives you this unit hyperbola. The inner product of vectors with themselves always equaling 1 here gives you this vertical line. The inner product of vectors with themselves always equaling 1 here gives you a circle. So the locus of vectors of magnitude 1 has these 3 different shapes for the 3 different geometries depending on what your inner product is, because inner product determines how you measure length to some degree. On the x-axis, length is always measured the same way. So essentially, if you want to measure length, you rotate by what you mean by rotation until your vector lies on the x-axis, and then you measure its length. And in that sense, they all measure length the same way. Okay. This is called elliptic measure of angle because you're marking out area with an ellipse. This is called parabolic measure of angle. Wait, there's no parabola here. I'll get to that. This is called hyperbolic measure of angle because you're marking out area with a hyperbola. It turns out that in Galilean geometry, what you want to think of as a circle is a parabola. If you define circle as like the locus of points equidistant, then you don't get a parabola. But there's another way of defining circle that gives you a parabola, and it's a wonderful tangent that I can't go on. But parabolic measure is essentially what you think of as normal distance measure. Because what you're measuring angle here is really the distance here. This is equaling angle because this is a unit away. So the slope is really just the height. So essentially, normally in Euclidean geometry, you measure length parabolically. I mean, it doesn't really have that much to do with parabolas, but it's just the name. Minkowskian geometry, you have hyperbolic measure of angle. Now let's think about this for a little while. What does this mean? Elliptic angle, we can rotate as far as we want, and we just get to 2 pi, right? That's as far as we can get, and then it starts looping around. We can keep shearing and shearing and shearing and get a greater and greater slope. But remember, the slope equals the angle, so we can have as big an angle as we want, right? Which is kind of cool. But the one thing we can't have is a vertical line, because that would equal an infinite angle, which you can't specify a line that has infinite angle. So then that brings us the question, wait, what if 2 points are separated vertically? You can't draw a line between them. So what about that axiom we had, that any 2 points determine a line? Well, it's kind of like we're not following the axioms, but the axioms are very general and have to do with more like, in the affine plane, you can always do this. Like, you can always draw a vertical line. I've drawn it in red. But, but in this specific case, our angle measure is undefined on such lines. So it's not really part of our geometry, even though it's still part of affine geometry. I don't know if this is really making sense, but it has to do with the topology of the affine plane. And all these live on the affine plane, so they exist. In Galilean geometry, we call them special lines. I'm completely serious. Anyway, now in Minkowskian geometry, things are even worse. You can't have lines of slope greater than 1, right? Because they won't intersect the hyperbola anywhere. So you have a lot of special lines in Minkowskian. But these are all still affine geometries. Oh, okay. Let's get to Minkowskian trigonometry. So it turns out that just based on the definition of Cauchy and Sage, if you have a unit hyperbola, the y value is the hyperbolic sine of theta measured hyperbolically, and this length, the x value, is the hyperbolic cosine of theta measured hyperbolically, which is twice the area here. That's just the definition of Cauchy and Sage. You can also define Cauchy and Sage algebraically in terms of exponentials. We won't really get into that. Excuse me. Now, I told you that the inner product of 2 vectors equals some function of the angle between them. In hyperbolic geometry, it's the hyperbolic cosine. Surprise. But this isn't actually hyperbolic geometry, but we're measuring angle hyperbolically, so that's why. And I'm assuming they're unit vectors, otherwise you multiply by 1. Anyway, so let's have a triangle. And I've carefully constructed this so that all these lines are valid lines of Minkowskian geometry. If you measure their slopes, they're all less than 1, I promise. So, using linear algebra and just like a lot of work, you get to this fact. But, I mean, anyone recognize this? It's just a law of cosines, right? Except I've added an h in it. And it basically, you just take your normal trigonometry laws and you put an h in where you need them. And make them all hyperbolic functions and it works. Which is pretty darn cool, I think. The law of sines is the same way. It's instead of sine of the angle over the length, it's sinh of the angle over the length. And it's like all holds. Alright, this is all well and dandy. And now is when the fun begins. So, we have this idea. Now, it turns out cosh as a function, you know, I'll just plot it over here, because I was negligent and didn't prepare this. Cosh looks something like this. We have 1 here, and it looks like that. Cosh is always greater than 1. It's the sum of cosh equals, if you really want to know, theta, that's a theta, equals sum of e to the negative x plus e to the x over 2. So essentially, out here, it grows exponentially in both directions. Anyway, the point is that it's always bigger than 1. So we can say that a squared is always greater than or equal to this side. Or less than equal, sorry, because this is a minus sign. And then you can factor this a squared is less than or equal to c minus b squared. And you get the fact that c is always greater than b plus a. Anyone see what's suspicious about this? You.
It's greater than or equal to.
Well, yeah, because like c could be lying on this line, and then it would be linear. But what's really suspicious about this is
No lower limit?
yes, in normal geometry, the shortest distance between 2 points is a line. What's going on here? The straight line is the longest distance between any triangle you make here is going to be shorter if you. Holy shit! This is like clearly we're doing something wrong, right? It turns out, no. Correct. And it all just comes down to how you measure your dimensions. You can measure a dimension with this guy, or you can measure a dimension with this guy. And it turns out that one of our dimensions is time and not space in this case. That's all that's going on. That's all that's going on. And what we have in Minkowskian geometry is just special relativity. Like, they were different in the inner product, right? We had positive x1 times x2 minus y1 times y2. Well, y was space and x was time, so they mix in this different way than two space terms would mix. I mean, this is a physical interpretation of it. Mathematicians wouldn't really care, like whatever. But like, I think that the fact that we've just stumbled upon special relativity is kind of cool because like Einstein got pretty famous for discovering this, and like we just stumbled upon it. So it turned out Minkowski discovered this geometry before Einstein did any sort of special relativity work. In fact, Minkowski was Einstein's math teacher. You.
Now, when you say the shortest distance, what do you mean by distance?
Oh, right. So it makes no sense to measure Euclidean distance in this space-time thing. The only really measure of separation between points. By the way, if a point is plotted on space and time, what does it represent? It represents a unique moment in space and time, which we call an event in physics, right? So what we're measuring by distance is just the amount of time elapsed on a clock that is on hand for both events. Now, as we know from relativity, if you go really fast, your clocks slow down. So if you go the slowest you possibly can, the most time will elapse on your clock between the two events. If you zip around, go to Pluto in between and then come back, Like, you're going to age less. That's special relativity. Less time is going to elapse on your clock. Thus, the longest distance between two events, the longest time between two events, is the path that takes no acceleration. That's another way of phrasing this. I mean, this is just a physical interpretation. The geometry is completely separate of the physics. Like, it just turns out that like geometry models reality for some reason. I don't know why. But if you have two space dimensions, then we have Euclidean geometry, and that models space pretty well as far as we can tell. If you have one time dimension, well, then you've got space-time. Anyway, so there's, yes.
Is there anything with two time dimensions?
Like, I don't see why not. I've never encountered it, though. Oh, I mean, yeah, probably. We're gonna get there, There's so many geometries. But like, if you have one space and two time dimensions, that's a three-dimensional geometry, and I'm only covering plane geometry, so. Anyway. So, yeah, that's what's going on with Minkowskian geometry. And there's a whole study, you can go and do a lot with Minkowskian geometry. It's one of my favorite geometries. But we're kind of, yeah, we've already reached the punchline, so. Let's talk about incidence probably. So remember Galilean geometry we talked about? So that only didn't have vertical lines. Minkowskian geometry didn't have all these lines, right? And then they Euclidean, Galilean, and Minkowskian have all the gray lines, right? Does it make sense? Okay. What was the point? Oh, Galilean geometry is just classical mechanics. It's like, well, the only speed you can't go at is infinity in classical mechanics. And so that's the only lines you don't have are ones of infinite slope, of infinite velocity. And the reason it's named Galilean geometry is because he was the first one, as far as we know, to realize that if you change frame of reference, like nothing changes. And this was because he was like, no guys, we're orbiting the sun. And people were like, wait, if we were orbiting the sun, we'd be like, whoa, we're moving around. And he's like, because the Earth is moving, we'd feel it, right? We must. But he was like, no, think about this. Oh dear. Think about this. You're in a boat, and you're sleeping, and it leaves port during the night. And it's moving really slowly. When you wake up, you don't realize it's moving because you're not accelerating, essentially, was what he was saying. That if you're not in an accelerating frame of reference, you can't know that you're moving. And he made a very complex thought analogy with birds and little critters. And he was trying to convince people, like, no, we're orbiting around the sun, but we don't feel it because we're all moving together. And the shear in space-time, like if we were to shear this, there we go, we add like a velocity to everything. We add a constant slope to everything. That's just changing your frame of reference. Now it turns out like he was missing some things, which is the way the space and time are connected, which is why we need Minkowskian geometry for actual physics. So Minkowskian geometry. Now, remember, we had a hyperbola. So this is saying the speed of light is 1, right? It has a slope of 1. Because that's the speed you can't ever get to, but you can get it. Now, the speed of light in traditional units is like really steep, right? So it basically looks like a straight line, the hyperbola. So locally, hyperbolic geometry is Galilean geometry. Because like the slope here is infinite, just like the slope of this line. Anyway. This is all just determining on what we wanted to take as our two-dimensional, functions of two-dimensional transformation, linear transformations with one determinant. Anyway, so we've got these properties. In Euclidean geometry, you can connect all points. In Galilean geometry, you can only not connect vertical points. In Minkowskian geometry, you can't connect lots of points. Now, points you can't connect, I'm just going to call, let's call them parallel points. Like, I know parallel talks about lines, but like, if two lines are parallel, they never connect. So, like, it makes sense, right? Parallel points, 0, 1, and infinity. Now, we're assuming that you've got a line, you pick a point not on the line, then how many points on the line are parallel to this point not on the line? 0, 1, and infinity. A good way of, there's sort of one direction that's not allowed, infinite directions that are not allowed. Now, all these geometries have one unique parallel line, because that has to do with how we're measuring distance, which really hasn't changed. We've changed our inner product, but along the x-axis, everything has stayed the same, so we're good. All right. So that's basically affine geometries for you, the 3 affine geometries, Euclidean, Galilean, and Minkowskian. One is space, one is non-relativistic mechanics, and one is relativistic mechanics. All right, now we're going to move on to projective geometry. And it's called projective for a reason, because it was studied when people started realizing, like, wait a second, things in the distance are smaller. And they started drawing these things and trying to figure out mathematically how this goes. And they're like, wait, we're like projecting the 3 dimensions onto 2 dimensions? That's why it's called projective geometry, because it's the geometry that came through that. But anyway, our axioms are now, we have the same 2 first axioms that nobody cares about. Now, 2 points determine a unique line, we had that before, and 2 lines determine a unique point. Wait, we had a parallelism axiom before, and now that's gone. That's because in perspective, like even parallel lines meet, right? They meet at a point, what's called a point at infinity, which doesn't make much mathematical sense when said that way, but basically you have no parallel lines in projective geometry. Now, I want you to notice, if let's say we're operating on a field that is infinite in order, so every line contains at least 2 points. We've got infinite number of points on every line. We've got infinite number of non-collinear points, okay? So both of these don't really get into. If I made up words for points and lines, how would you be able to tell which axiom was about which points and lines? Like, there are 2 lines determine a unique point, 2 points determine a unique line. Like, they're completely symmetric. So, like, what is the difference between points and lines here? It's kind of interesting, because there isn't any, actually. This is a model of finite projective geometry. You can, every line every line has 3 points on it, and yeah.
So you have the last 2 axioms that are interchangeable, so what's the line, what's the point? But since you have the first 2 axioms there.
Well, maybe they're distinguishable in the finite case. They're not distinguishable in the infinite case.
Okay.
But we'll get to that. So, modeling projective geometry. How this is done is you essentially, we're working in R3 now, and we'll take points are lines through the origin. So I just said points through the lines, but don't worry. Because I'm constraining them to line origin. We go through the origin. So here's our set of axes. These are, a point is here. Essentially, we say any two points in R3 are the same if they're a multiple of each other, like they're equivalent. We're defining an equivalence relation on all the points in R3 such that this is the case. Like all these points we consider to be exactly the same, and these ones are down here too. So like this whole line is just one point. And if you were to like put a surface here, like a plane, you would intersect in a unique point, and that would be your point. Now, lines then are just planes through the origin. A plane that contains, so if you have 2 points, this line through the origin and this line through the origin, there's a unique plane that contains them, which is the line that goes through the 2 points. You essentially just upped everything by a dimension, and then said that they have to go through the origin. This is crazy topological stuff, and I don't know if any of you are familiar with this sort of diagram, but like you try to put this arrow on this arrow and this arrow on this arrow at the same time to get your projective plane topologically. It looks like this guy, which may not be any easier to understand. You can't do it in 3 dimensions without self-intersection. It's like this. You know you have a Mobius strip. It has one edge, right? And it looks like this. Right? This is surface that goes behind the curve. It's a Mobius strip. It has one edge, right? You go around and around and around. A circle also has one edge, which is its circumference. Imagine you had a circle that had the same circumference as this Mobius strip, and you just will like glue them together and just went around. That's how you get a projective plane topologically, and you can't do it because you'd have to have the circle intersect as well. But topologically, that's a projective plane. It's really nasty. But anyway, what we're going to do is we're just going to choose various surfaces that they can intersect. Remember how the inner product had to be these quadratic functions? Well, basically we're going to only choose conic sections for our, sorry. We're quadratic functions of x and y as our surfaces for intersection. The most straightforward is x squared plus y squared equals 1. This is called elliptic geometry. So points are now antipodal points of the sphere. So we have a sphere, and a line through the origin intersects it in two places that are on opposite ends of the, like the North Pole and the South Pole. And that's one point of our geometry. Like it's got two places, but let's see what's positive and negative. We're considering doing the same thing. And the beautiful thing about this is that, and if we're talking about planes through the origin, we could talk about them as their normal vector. So we represent points by some sort of vector from the origin. Lines are also vectors from the origin that just represent, that are just normal to the plane that goes through the origin. If we have points A and B, and we want to figure out what line goes through them, both, what vector is normal to both of them? They're a cross product. Right, we all know what cross products are, right? Okay. If we want to figure out the angle between two lines, well, you say, well, look at the surface of the sphere, look at the tangents vectors here and here, and see what the angle between them is. Well, that's just the angle between the normal vectors of the planes. You can show that pretty easily. So, angle between two lines is just the inverse cosine of their inner product. Like, this is all just becomes linear algebra. Everything in elliptic geometry is just basic linear algebra with cross products and dot products. It's like really easy and really wonderful. But at the same time, it's not boring. So, we have the fact that the distance between 2 points is the inverse cosine of the point vector 1 and point vector 2. Because how do we want to define distance? I'll go back to the previous slide. Distance is really, well, it's this arc length here, right? But arc length is basically angle. That's how radians were defined, right? The arc length between here, assuming these are normal unit vectors, is just the angle measured in radians. So the distance between 2 points is really the angle between the vectors that represent them. And the angle between 2 lines is the angle between the vectors that represent them. So everything is just measured in terms of radians, distance and angle. It's wonderful. Because there's no telling what's a point and what's a line. Because there's no difference between the point and the line. If you have a point, it can represent a point, or it could represent the line, the great circle that goes around it. There's absolutely no difference. And everything is just cross and dot products. It's wonderfully symmetric. Alright. You measure angle and distance exactly the same way. This is what is known as a self-dual geometry. A geometry in which points and lines behave exactly the same way. Now notice, if we have 2 lines, which a plane intersecting the circle is a great circle, like an equator, right? If you have any 2 of them, they're going to intersect at 2 antipodal points. You can probably see that intuitively. So there are no such thing as parallel lines. And there are no such thing as parallel points. They both behave exactly the same way. So what's cool about this is that any theorem in elliptic geometry, you take the points and you can write a computer program that does this. You take points and you change them out for lines. You take intersection between 2 lines and you make it the line that goes through the 2 points. You do this systematically, like literally a computer program to do this, and you get a completely different theorem, but it's like by default true because you proved the first one, that it has to be true because points and lines behave exactly the same way. An intersection and constructing a line between 2 points are exactly the same operation. It's just cross products. So like essentially in elliptic geometry, you get 2 theorems for the price of 1 every time. You prove one, and you've proved another one just because points and lines are exactly the same. Elliptic trigonometry is also simple. You just have trigonometric functions in front of everything. The law of sines is you measure length in terms of the sine of this, not the length. So it's like sine over sine, sine over sine. Everything's in terms of sine. Like, yeah.
Isn't that how Fermat's last theorem was proved?
I actually have no idea.
Yeah, I think because the idea was actually they had to prove that one proof, like in one realm, proves the other in the other realm, and that was the thing that like linked, because you can express the equation as
that makes sense. Okay. Anyway, the elliptic trigonometry becomes really simple. Everything is inside of some sort of trigonometric function. Now note, as we make this triangle smaller, it gets really, really small, the lengths get small, the angles don't approach 0. So this stays sine A, sine B, sine C. But sine C, when little c is really small, is basically C. So as we make this really small, this becomes the Euclidean law of sines. So elliptic geometry is locally Euclidean geometry, just like Minkowskian geometry was locally Galilean geometry. One thing that's really weird about elliptic geometry is it's not scale independent. It's scale dependent. You can't just multiply the size of a triangle by 2 and have it be the same side angle relationship. As you can see here, we have a triangle with 2 90 degrees because they're both on the equator and one's at the North Pole, right? So clearly the angles no longer add to 180. They add to much more than that. The bigger the triangle, the bigger the angles. The bigger your shape, the bigger the angles. You have a sort of an absolute scale on your geometry, which is completely different from Euclidean geometry in a very important way. And what's really cool about this, and you can prove this fairly straightforward by talking about like the fraction of the circle that is carved out by that what's called a lumen shape there. Anyway, you can prove that the area of the triangle that's colored in is simply equal to the amount by which the angles sum to more than pi. That's probably negative of what it should be. Because it's never more than pi, so okay, error there. But you see what I mean? That's error. I mean area, assuming that it's of unit radius. Right? We have the right units on everything. Okay. All right. Now let's move on to hyperbolic geometry. So we have the same sort of lines of points as we did for elliptic geometry. Everything goes through the origin. Instead of intersecting a circle, though, instead of intersecting a unit circle, we're going to intersect the unit hyperboloid. Right? Like, why not? It's the other main quadratic sort of surface. Of course, there's more than one unit hyperboloid. We could have the hyperboloid of one sheet that would look like that, right? It would look, and that would give you co-hyperbolic geometry, I think. But like, I don't have time to do all the geometries. Okay, now the Klein model, basically, it's really, so if we're talking about where things lie on a hyperboloid, that's great, it's two-dimensional, we have a plane geometry. But it's really hard to flatten a hyperboloid. So we talk about things in terms of where they intersect the hyperboloid, but we look at them based on where they intersect the plane z equals 1, because that's a plane, we can actually look at it on like a screen or on a piece of paper. So that's what the Klein model of hyperbolic geometry is referring to. Alright, how do we measure distance? Well, our points are vectors from the origin. And before, in elliptic geometry, we measured distance based on the angle between them. Now here we're just doing the same thing, only it doesn't make sense to measure, we just measure angle elliptically now. So these are evenly spaced points. An angle is measured based on the area of this shape here, remember? Okay. So now look at what happens towards the edge. We know that it's going to intersect the hyperboloid, so it's never going to leave the unit circle in the line in the plane z equals 1. So everything is contained inside this circle where it intersects, because it has to intersect the hyperboloid. But things get really close towards the edge, even though they're equidistant. Yeah, but this is just how we're measuring distance, because we're measuring distance hyperbolically now. Before we were measuring distance elliptically, now we're measuring distance hyperbolically. All right, measuring angle. Well, we measure angle, these are a little hard to understand. But here we have a hyperboloid, right? This is a hyperboloid. And we have two planes that go through the origin. They make a line of intersection with the hyperboloid. And if we look at the tangent vectors on the hyperboloid, we can talk about the Euclidean angle between them, right? Or the elliptic angle between them. That makes sense. Right here, we have two perpendicular planes, and they make a perpendicular lines in the geometry. Here's another way of seeing it. This plane is the green line. People see, it's kind of hard to get these figures to be clear. It really is. I didn't spend a good amount of time trying my best. So these are two different views on the same thing. But the thing is about this is that hyperbolic geometry is really weird in the way it measures angle. And basically, it's because of this. If you have two intersecting planes, and you look at their intersection with a plane that's perpendicular to both of them, you just get perpendicular lines. If you tilt it, okay, I'm not able to draw this clearly. Oh, once you start tilting things, even though the planes are perpendicular, the lines they make no longer become perpendicular. So let's see if this can be seen. So this plane is again the green intersection with the hyperboloid. And we have two different planes, one blue and one making red, that are both perpendicular to it. But for the red one, it's tilted with respect to the hyperboloid sheet now. So the angle that the intersections make is acute, no longer perpendicular. Even though this plane and this plane are perpendicular. Like I promised you, and I made this so that they are perpendicular. This line is perpendicular, but these two lines aren't. They're acute. Basically, as you get further away from the center, angles get smaller. That's just what happens. It's like the opposite of elliptic geometry, where angles get bigger as your shapes get bigger. Angles get smaller as your shapes get bigger. And the conclusion is that angle is strange. So, what does this look like in the Klein model? We had the blue line, the green line, and the red line, and that just comes up to this. Now, in the Klein model, they look perpendicular. But you can't measure angle anywhere other than here in the Klein model. You're measuring angle elliptically, but to measure it, remember in Minkowskian geometry, to measure distance, we had to Lorentz transform everything so that it was on the x-axis, and then we can measure distance? Here, we have to hyperbolically translate this point here, and then we can measure angle. Because the figure doesn't produce, this model doesn't produce angle in terms of radians and stuff when it's not at the center. That's all this means. Now, what other effects does this have? So this is an acute angle here, even though it looks perpendicular in the Klein model. That's just the way the Klein model works. Well, the lines end when they hit the edge of the circle, right? Because you have to intersect the hyperboloid, so they can't go anywhere past that. So, and lines that just intersect at the edge, like the blue line and the two red lines, never actually meet, right? They meet at infinity, if you want to call it that. So those lines are called parallel lines. So the blue line is parallel with both the red lines. What about the yellow lines? They never even get close to meeting. Those are called hyperparallel lines. Basically, given a line, the blue line, and a point not on the line, we have an infinite number of lines that are parallel to it. It's based on the way we've constructed this. Because we're restricting our view to things that intersect this unit hyperboloid. It is a projective geometry, and so there's basic projective axioms that said all lines intersect still hold in some degree, but they don't hold on the hyperboloid.
Does hyperparallel have any relation to skew lines in 3D space?
No. So, what is going on? So, I've talked about the fact that this is scale dependent. So if you make a shape bigger, the angles get smaller. What does that mean? Well, it means in hyperbolic geometry, you can tessellate a heptagon. If you make it big enough, the angles will be right so that these are all 7-sided figures, and they tessellate on hyperbolic surfaces. Not only that, but if you had an 11-gon and you made it big enough, the angles would become small enough that you could tessellate them too. You can tessellate in hyperbolic geometry any n-gon you want. And that's one of the things that I think is the coolest thing about hyperbolic geometry. Basically the punchline for hyperbolic geometry. You can tessellate any gons. So you just need to make them big enough. So it turns out Escher, sort of discovered hyperbolic geometry artistically without knowing what he was doing. He was a genius, basically, is all you can draw from that. He created hyperbolic tessellations just because, oh, look at these cool patterns I found. He didn't know anything about hyperbolic geometry. Anyway, so now we're back to incidence properties. We have 3 geometries. Euclidean has no parallel points and 1 parallel line. Spherical has no parallel points and no parallel lines, right? Any 2 lines intersect. And then hyperbolic geometry has no parallel points, but infinitely many parallel lines. Alright. We've had 3 different projective geometries and 3 different affine geometries with various permutations of 1, 0, and infinity and parallel points and parallel lines. It turns out, so there's essentially 3 different ways to measure things. You can measure things elliptically, parabolically, or hyperbolically. And that leads to 1, 0, and infinity in the parallel lines and the parallel points, whether you're measuring distance or angle that way. So essentially, there's 9 different plane geometries, and that's it. These are the Cayley-Klein geometries, the Cayley-Klein plane geometries. You can measure angle elliptically, parabolically, or hyperbolically. You can measure length elliptically, parabolically, or... Anyway, and this gives us 9 different geometries. If we measure length parabolically and angle elliptically, we have Euclidean geometry, normal geometry. If we measure them both parabolically, we have Galilean geometry. We measure angle hyperbolically and length parabolically, we have Minkowskian geometry. Now, the geometries that have the same type of angle measure and length measure are self-dual, in that you always get 1 theorem for the price of 2 in all of these 3. It's not just elliptic geometry, it's also Galilean geometry. I never really talked about it because I didn't really have time, but it's the same. And also doubly hyperbolic geometry, which I don't even know a good model for it off the top of my head. But it would be the case in doubly hyperbolic geometry too. Now it turns out, if you come up with a theorem of Minkowskian geometry, which, there's a lot of theorems of Minkowskian geometry because it's relativistic physics, and anything that's known about relativistic physics is Minkowskian geometry. So there's a lot of stuff about Minkowskian geometry. If you switch out points and lines, just interchange them, you get a theorem in co-Minkowskian geometry that's guaranteed to be true. Because the measures are just switched. So this is the dual of Minkowskian geometry. And any theorem in Minkowskian geometry has a similar thing that's true in co-Minkowskian geometry. So you kind of only have half of these, mathematically. But anyway, if we talk about incidence properties, we have this. Parallels, lines, and points. So elliptic has none. As we change the length measure from elliptic to hyperbolic, this should still be hyperbolic. We go from parallel lines going 0, 1 to infinity. As we go from angle measure, elliptic, parabolic, and hyperbolic, we go parallel points, 0, 1, and infinity. And we just have all the different combinations of these. And these are the 9 plane geometries. These are the non-Euclidean geometries. That's it for my talk. Yeah, I didn't get to talk about a lot of these geometries. There's so many topics I left out, it's ridiculous. Because this was a semester-long course, and you covered a lot of stuff in a semester. And it was like always jumping from topic to topic. You can talk about all these geometries in terms of different types of complex numbers. You thought there was only one type of complex number. Turns out there's 3 different types. And they correspond to different geometries here.
What's your favorite tangent to go off on?
Probably complex numbers.
Okay.
Because complex numbers model elliptic geometry, Euclidean geometry really well. You multiply and you get a Euclidean rotation. And you can also translate by just adding them together. Basically, Euclidean geometry is complex numbers. What about Galilean geometry or Minkowskian geometry? It turns out there's other types of complex numbers called split complex numbers and something else. Basically, they're not mentioned anywhere because they're just different ways of thinking about all of the. This is called classical geometry because it's a solved problem in mathematics. So you don't learn about it, and there's like very little information about it. The textbook for this class was out of print from the 50s. And so there's no textbook because nobody cares about it anymore, even though it's pretty cool. So basically, you can define the imaginary unit J, not J in electrical engineering, but J to be the thing that when squared equals 1 but isn't 1. It's not a real number, but when you square it, it equals 1. And that gives you Minkowskian geometry. You can all the formulas hold. E to the j theta equals cosh theta plus j sinh theta. Everything just becomes hyperbolic, and all the Fourier series happen the same way as would, and everything works the same way. Not only that, but with this tool, you can turn almost all theorems in Euclidean geometry into theorems in Minkowskian geometry, as long as you can phrase them in terms of complex numbers, and then you just put j in for I, where j is this split complex number, which has slightly different properties than I, but is still complex. You get this valid theorem in Minkowskian geometry, which is essentially turning a theorem that's about space into a theorem that's about space-time. This is really cool. I didn't have any time to talk about it. This is what my final project was on when I did this class. Because we didn't have any time to talk about it in the class either.
Share space.
Does that complex number can have anything to do with quaternions?
Not that I know of. So it turns out there's another thing for Galilean geometry. You say, oh, we're going to find a complex number, and we usually call it epsilon, which is not a real number, but when squared equals 0. And then you get Galilean geometry. Now, what's pretty cool is to then look at what is the Mandelbrot set look on these different complex fields? It turns out it's only a fractal in Euclidean geometry. You get a square of a diamond in Galilean and Minkowskian geometry. There's so much to talk about. And also vectors. Vectors is the abstract relation between 2 points. Instead of talking about vectors, you could talk about doublets, which is the abstract relationship between 2 rays. Where instead of having angle be the primary thing that you're concerned about, position doesn't matter for vectors, right? It's just direction. In doublets, it's just angle and position that matter. If you translate it, you get a different doublet. But you're essentially forming things with rays and you get the same vector spaces. It's just everything's. Anyway, it's another sort of duality in mathematics that again nobody cares about because it's vector spaces are good enough. We don't need this thing that's mathematically equivalent to vector spaces, but is pictured differently. But it's kind of cool anyway. What else did I talk about? Oh, you can talk about these all in terms of abstract algebra and what their symmetry groups are. And that's another topic I did. Anyway, you can go on and on. But they're all solved problems again, so nobody really cares.
What about non-affine geometries?
Non-affine geometries? Well, projective geometries aren't affine.
Okay.
So these are the affine geometries. And these are the projective geometries. Let's call them. And these are. They're co this and co that and doubly this. People realized that there were 9 geometries after they'd already sort of set up these other geometries and given them names. And they're like, oh, there's this geometry too then. But again, like because anything in hyperbolic geometry proves something in cohyperbolic geometry, like there's no need to study both. But the models look completely differently, and somehow all the hyperbolic stuff ends up dealing with space-time in some way, because time behaves hyperbolically and space behaves elliptically or parabolically. Like there's something going on there, and I don't really understand it. But anyway, those are the non-Euclidean Klein geometries. Klein, of course, of the Klein bottle. Cayley, I don't know what else he did, but Cayley did. That's basically all I know about geometry.
How long would it take to explain the parabola in parabolic?
Not too long. So, essentially, when you define a circle, you define it as a locus of points that are equidistant from the center, right? You can also define it as given 2 points, the locus of points where that angle is constant. And that gives you a parabola in elliptic. This gives you a circle in a circle in Euclidean geometry and a parabola in hyperbolic geometry, in Minkowskian geometry, just as the distance thing did. But in Galilean geometry, it gives you a parabola instead of the 2 vertical lines that you would get otherwise. And it turns out when you talk about Galilean rotation, you don't really just mean a shear, you mean a shear plus a little translation. And it's because one of the surfaces I didn't talk about was if you just took a plane in your projective geometry, and that essentially gives you affine geometry, because the affine plane is just z equals 1 plane in projective space. I don't have time to explain it. But so basically you can have translations in matrices because it's really just a shear and a z, right? I don't have time to explain it, but so, hold on. Essentially, it's basically a shear that maps shears map parabolas into themselves. It just moves their center around. So then you have to translate to make up for that, to essentially rotate through the parabola. And you can actually encode a translation in a matrix if you just add another dimension, is basically all that's going on. And then it becomes it's like a shear plus a translation thing. That's your rotation in Galilean geometry. Whatever. That's why it's called parabolic. Because parabolas are much more interesting than 2 vertical lines, so that's what they wanted their circles to be. As far as I know. Also, finite geometry, when I talk about fields and stuff, like you can go all the way with the group theory analogy and talk about field extensions, which are an interesting part of abstract algebra. And that was my first exposure to abstract algebra was geometry, because you actually can go pretty far into abstract algebra just by studying finite geometries. But obviously no time for that today.